So, hello everybody for this BoF. Thank you for coming. And I'd also like to take the occasion to thank all the DebConf organizer, both local and global, and video team and volunteers and everybody. I'm really enjoying this DebConf. And we're here to speak a little bit about Bootstrappable Debian, and I'll explain in a little bit what I mean by that, and why I personally believe that's interesting topic. Yeah, and yeah, there are. I've recently become interested into this topic, and I have a couple of projects on myself about which I'll speak to you. But there are also many other projects by other people, and I'll also try to tell you something about all those projects, although I'm not as knowledgeable and expert on these other projects as I am on mine. So if someone else is able to contribute, this is a BoF, so it's perfectly fine to interrupt and to say what can be helpful for the discussion. I think that it could be useful if someone can take notes on Gobi, if someone can volunteer for that, or see, because I know that, for example, there are people that are that will be available on IRC and who could not come to the DebConf, and so it might be useful if someone can monitor that and relay relevant things to the audience. I've created a document like Bootstrappable Debian BoF, not very original, and there is a little structure there, so it should be easier to. Okay, so now to the topic. So the initial question for my talk is, for my BoF is, how do I make yogurt? And you might know that the recipe to make yogurt is take some yogurt and add milk to that and let that stay for a while. Okay, and you'll have more yogurt. But you cannot, I mean, we don't know how to make yogurt if you don't have some yogurt already, okay? And that is a kind of thing that also happens in Debian. So we're probably used to think to Debian as a big bottle of source packages. And then there is a process by which these source packages are at some point converted into binary packages. And that's what our users and we ourselves use when we install and use Debian. But the point is that the process is a little different. We have a lot of source packages, of course. But in order to compile binary packages, we already need some binary packages, the dependencies for the source packages. Okay. So when we already have a binary distribution of Debian and we have some more source packages, we can compile either other binary packages. But if we only have the source packages, we're not able to devise any binary package because we don't have any way to have at least an essential system, to have build essential and possibly other build dependencies. And so in this sense, Debian is not bootstrappable. That's what I mean when I say that when I speak about bootstrappability. So why you think that this is an issue? This is something we should care about. So there are some philosophical and maybe freedom-related reasons. For example, I tend to think Debian that as primarily is source packages, and then secondarily is binary packages. And I don't know if you agree with this view, but to me that's pretty important. Why is that important? Because Debian is important to me because it's free software. And free software means that, of course, as you know, I can do a lot of things, including using, distributing, but I can study, can adapt and enhance this software. And I cannot do that on binary packages. I can only do that on source packages. Okay. And of course, each time as a developer, I do something with packages, I work with sources. Then there are some computers, some buildees that will compile the packages for me, but that's I mean that's not what I am doing. There are reasons that are related to security. There is this famous speech by Ken Thompson on trusting trust. And for those who know what this is about, the thing that Thompson presents is the following. Suppose that we want to introduce a bug in a computer program. Then maybe we do not want to change the source because someone could find that bug or that security pitfall. Then what we do, we change the compiler. Because of course, the program cannot be used if it's not compiled. So we just take the compiler and change it to introduce a miscompilation when that particular program is built. But then one could discover this problem by looking at the compiler source code. But since the compiler itself is compiled, then we can change the source of the compiler by adding, well, first a feature. Let's call it feature, so that when it compiles the program that I want to be bugged, it introduces the bug. And then I also modify it so that when it compiles the compiler, it introduces into the compiler itself a feature, again, between quotation marks, that makes so that the new built compiler again has this property of introducing the bug in the software and the bug in the compiler itself. And if I do that, the bug becomes completely invisible. It exists into the binary, and each time I recompile the compiler, it gets propagated in a new binary, but it's not visible in the source code anymore. So it's undetectable. It's virtually undetectable. And in line of principle, I'm not claiming this is happening, but in line of principle, that will definitely happen with our compilers in Debian as well, because we are not being I mean, all of the compilers we have in today's Debian are compiled with the compiler that were in yesterday's Debian, which are compiled with the compiler that were the day even before in Debian, and so on, up to very long time ago. I don't know when exactly, but at some point they were bootstrapped. And other practical reasons about bootstrapability is that we do some bootstrapping every now and then. For example, when we bootstrap a new architecture, or when we bootstrap a new language that depends on itself for compiling. And this is usually known as a very painful thing, and it would be nice if it wasn't. This is in particularly happens for people who want to produce embedded distribution out of Debian, because usually for embedded distribution you want to cross-compile thing, you want to cross-bootstrap your distribution. And so it's nice to have tools that make it easy to do so. And also, this is of course related to the first thing I was saying. I think that it's nice to be sure that our current binary, the big bottle of binary packages we have at some point in time is actually built from the same sources we have at that point in time. While at this point, something differently could happen. For example, if I have a program depends on a static libraries, at some point it gets compiled and it uses that current version of the static libraries. Then many other versions of that static libraries are uploaded to the archive. But since the program doesn't have a binary dependency on the library because it's a static library, the program is never recompiled. And so first, it has possibly updated, possibly unsecure, possibly whatever code. Second, this might raise some legal concern because it might be that we're not distributing anymore the source that was actually used to generate that binary package, which is against our free software guideline promise, and possibly also not actually legal. So I'd like to first state what I call this humble ambition. I'd like to, at some point in the future, possibly in the far future, because it's not an easy thing, it will be possible to just take the whole bunch of source packages that are in Debian, plus something already compiled, because of course you cannot start for at least something that is already compiled, since you cannot feed sources to a CPU. But that thing should be as little as possible. And I would like that from these two things, it would be possible to recompile the whole binary distribution of Debian. And of course, one might ask, well, okay, now if suppose we can do this thing, now we have the binary packages that are already in Debian, and we create another set of binary packages, and how do you choose which one to keep? Well, of course, we're dreaming, so we can also assume that Debian is fully reproducibly buildable. And so we know that these two sets are actually the same. So we have just checked that Debian is updated, is currently building from its own source packages and not from something else from the past. And we're happy, I believe. That would be a very nice property for the reason I told you. So where are we now? I would like to present the projects. A couple of them are from me, and others are from other people. I would like to present what's the state of the art, at least from the researches I did and what I got from speaking with other people. And so that we know how we can improve. And first of all, I would like to introduce these 4 stages of binary bootstrapping. This is a thing I came up with yesterday evening. And so, it could be totally something completely useless, completely irrelevant. But I think that at least for me, it helps to sort out a way of thinking at this process and understanding, and having some common language to refer at this. And of course, we'll see if you agree with my point of view. So at the beginning, we have what I called inorganic matter. We have in the most uncompiled stage possible. We don't have a kernel, we don't have standard environment, we don't have basically any built binaries. Again, as I said, we cannot start with no binaries at all because we need something to feed to the CPU. So let's assume we just have a very little binary, as little as possible so that it can be audited even if it's a binary. Usually it's very difficult to audit and to check if a binary code, if a compiled code is doing what it pretends to do. Maybe if it's not more than a few kilobytes, then we can do that anyway. We can disassemble and check it and understand its property. Then there is a second stage that's called organic molecules. And let's say that starting from this very little compiler, we have managed to compile a kernel, and of course we always need to have at least a simple compiler to go forward. Otherwise, we cannot compile anything more. But we don't have yet standard utilities that we assume to have in a system. And we don't have a concept of distribution, so we don't have DPKG or all the nice tools that make up Debian. If you go a little forward, we arrive to Reallife. We finally have some standard user space, some distribution essential tools. I'd like to think that Prokaryotes is more or less what happens in a Debian system when you install nothing but the essential and build essential packages, more or less. Do not take, please, this 4 stages as precise specification. For me, they're just a way of thinking, generic idea of what stage a bootstrapping procedure might be. And then you have Reallife, which is what we usually have on a Debian system. We have the kernel, we have the distribution, we have a lot of, virtually all packages available. This, of course, these stages always only refer to binary packages. Access to source is, of course, always presumed to be unlimited because you believe that sources are the thing that you can audit. So it's not a problem to have sources. The problem is have binaries that you cannot check. So let's go to some efforts that there have been, and at least those that I knew of. to cover some of the segments of that scale that I just presented to you. The first two will not be Debian related, then the other will be built and meant for Debian. So the first one I've mentioned is GNU Geeks, which is a Linux distribution. Well, Geeks is a package manager, and Geeks SD is a distribution based on this package. Although in line of principle, Geeks, the package manager itself can be installed on top of another distribution, and it does also some features to make it that you can install it as non-root and to manage it independently of the main package manager. So one of the things GNU Geeks developer emphasize is reproducibility and bootstrappability. Sorry. So apart from a little relative little set of sources of packages, sorry, at the beginning of the dependency graph, which are close or more or less something similar to what we call build essential. Apart of that, all the rest is bootstrapped from those. So there are no dependency cycles, and you can actually take a topological order for the dependency relation and build one after the other all the packages, while with build depending only on previous packages and on this initial set. So that's a very nice property. It corresponds more or less to what we call the prokaryote to eukaryote progression, because you of course assume to already have something close to our build essential. So you're covering the last stage of the scale I mentioned before. They would like to do some more better. That is, cover at one step below, which is going from organic to prokaryote life, and so they have this other project that is called MESS, which is basically an effort to reduce this bootstrapping seed to something as little as possible. There's maybe like only a very simple C compiler from which you iteratively bootstrap the GCC toolchain plus binutils plus glibc. Then let's come to Debian things. Again, for Debian is currently not able to do the prokaryote to eukaryote progression, meaning that if you install only build essential, there will be a lot of packages that you cannot build because there are cyclic dependencies. So you do not know where to cut the cycle. You cannot cut the cycle at any point currently. So there is this tool called Botch, written by Johannes Schauer, which basically takes the build depends graph and try to extract some information. In particular, find the strongly connected components, so we know where the problems are, and try to understand where it might be sensible to cut. Of course, we know that in Debian we have a tool which is the build profiles, so that even if a package to be compiled properly should require a lot of dependencies, you can maybe compile the crippled down but somehow sufficient version of that package by giving up on a few dependencies, so avoiding some compilation steps. And so you can try to find, with this tool, you can try to find where it might be sensible to cut some dependencies, and then create some build profile that takes some lighter dependencies and basically helps the process of bootstrapping. With this tool, there are these pages, bootstrap.debian.net, that are generated. I think that unfortunately this whole thing is a little bit underdocumented. It also might be that I've had enough time to check out everything, but yeah, currently I'm not understanding everything that this. I mean, it seems to be a very powerful tool, and I'm not understanding everything it's able to do. Again, This, as I said, covered the prokaryote to eukaryote stage. And again, it would be nice at some point to go a little below. Debian, well, one approach that has been tested in Debian by Helmut Rohne is this tool called RebootStrop, which is a little bit different because it doesn't do organic to prokaryote, as mentioned before. But it does little. It assumes to have a full distribution already there, but for another architecture. So suppose you already have AMD64, which is most typical, and you want to rebootstrap, let's say ARM or ARM64, whatever you want. Then you can try to use RebootStrop, which basically will try to set up a cross toolchain for that distribution, and then start building its essential and build essential packages on whatever is needed to reach what we might consider a prokaryote stage. And it is routinely tested on Debian's Jenkins instance. There are currently a lot of red light, but I mean there are also some green lights, and I mean it's a I'd like to be able to say something more in depth about this tool, but yeah, unfortunately, maybe we'll have some occasion to discussion because I saw that Helmut should be on IRC. And in the meantime, let me finish speaking about the other tools. And now I arrive to the thing I've been working into, and which were my initial, I mean, the door through which I got to know this world, so I know a little bit more. So NBS, which is for N Bootstrap, meaning that at the beginning I had an idea of what the letter N was meant to mean. BS is for Bootstrap, but then I forgot. I mean, 2 hours having invented the acronym, I forgot what that N was about. So it's now N Bootstrap. Sorry about that. And it tries to do the organic to prokaryote step. It's very far from being able to do that at the moment. But basically, assume I have a Debian, a running Linux kernel, or a chroot for testing, and that only contains TCC, the tiny C compiler, and Musl as libc. Let's see how many other binaries I can compile. We're not speaking. I'm not speaking on Debian packages at this point because it's so early that I don't even have Debian standard tools like dpkg, dpkg-dev, and whatever. And but I'm trying to build the first binaries that should at some point make. I mean, which at some point I should be able to build also Debian tools, and that would mean that I've more or less reached the prokaryote stage. And then there is also another. Another project I've been working on that, to my knowledge, is the only one that is trying to actually tackle the kernelless step, the first step of my scale where you don't even have a kernel. So you're actually running at ring 0. SMC is called by, I mean, it's called directly by a bootloader. I have a bias calls bootloader, bootloader loads and calls directly SMC. And it tries, again, it's not really there yet, but it already does something interesting. It tries to bootstrap a Linux kernel, starting from such a minimal environment. So, and nice thing, it works on real hardware. I mean, it doesn't work, meaning that it doesn't reach a Linux kernel, but what work for the moment already also work on a real hardware. Usually I test it on a virtual machine, but every now and then I do a real hardware test and it works. So this is a BoF, so I have some additional slides, and there is also some additional time. But I didn't want to. I mean, this is a BoF. I would also like to have some interaction if some of you have something to say. And otherwise, if you want, I can also go especially to my projects, because are basically the ones on about which I'm able to say something more and tell you something more about what is currently implemented. So, but before that, if anybody of you has some question or thoughts or already other interesting projects that you would like to mention, please feel free. Yeah. Also, if you think that, I mean, what I've been saying has a value, is something, I mean, interesting, please. I know you.
I wonder what ASMC does. How does it work? Can you give us a walkthrough? I mean, what happens if you start it?
Yeah. Yeah, but I can repeat now the question. So the point is, how does ASMC? I still have to decide how to pronounce it. Yeah. Yeah. Let's try to explain a little bit more what it does. So yeah, it basically it is a very little program at the beginning. It just like less than 6 kilobytes worth of binary code. It is written for i386 for the moment, and it might be considered a kernel, but so basic that it doesn't do most of what kernels do. Actually, most of its size is actually used to implement a compiler, because as I was saying before, you cannot at any stage you need a compiler to go forward. Otherwise, there's no way to bootstrap anything more. And so I had this problem that I had to implement a compiler in as little space as possible. And well, we have usually used C for low level. I mean, it's used for many things, but usually it's one of the obvious choice for low level projects. But C is a quite complicated language, so it's difficult to write a very small compiler for C. So I tried to think, okay, how can I invent a language that is as close to C as possible, because it is the language that I know that people use, but is easy to write a compiler for. And I basically identified 3, or actually 2.5 things that make C complicated, and removed them to have a language that I think it's good for this step, and I call that G, because G is similar to C. And so the 3 things that I changed are these 3. First, I adopted reverse Polish notation instead of the complicated syntax that C has for expressions, which is difficult to parse as precedences, strange rules, and whatever. Well, RPN is very, very, very easy to parse. You just look at them and push things on a stack. And then the other complicated thing in C is the type system. There are a lot of types. There are structures. There are unions. There are. It's very complicated to. Just to write a parser for a type definition for the type declaration is complicated. So I decided, well, I need one type, which is int, that also works as a pointer to whatever, including pointer to function. And then you decide what a variable is each time, depending as you use it. And then there is the third thing, which is actually not that important. It's also simplification, but not that important, which is lexing. I just decided that tokens are split on spaces and nothing else.
So
yes.
Staying with your implementation of G, and you only have an int, is your int a fixed size for every architecture?
No, the point is currently there is only architecture that is supported by G, which is i386.
So is your int 32-bit, 64-bit, 8-bit?
32.
It's always an int 32.
Yeah.
And do you intend for it to always be an int 32? For other platforms?
Yeah, I haven't really tackled this. This is, of course, an interesting question, and currently I've decided that that's the only platform I'm tackling, and so I haven't really tackled the problem yet.
So,
so
you would anticipate later on cross-compiling from one architecture to the other using this, or would you just use this to bootstrap a new architecture?
I'd say that what I've been thinking for the moment is that you first bootstrap i386, and then you use that to cross bootstrap. But that's just a thought for the moment, because nothing of this matter applies. I think that if I were to port G to other architectures, I'd want int to be its natural integer size, and especially pointer size, because I also have to use them as pointers. And but I haven't really thought about that. Of course, since this thing is so baked in the G language, you do not expect G program to be portable at all, because you actually encode in the program the structure offsets, so they're not portable. After all, if G is if what you want to write with on G is basically a compiler, that's not portable anyway, because you have to target a different language anyway. So for the moment, I've decided that's not a too bad design. I mean, the point here is that number. Of course, if it didn't have this constraint, I would have taken very different decisions. But that's what I wanted to do for the moment.
And to ask the same question again, that particular number of 6K, is this because you can sit inside effectively cache inside an i686, so you don't need to bootstrap the memory architecture?
No, I mean that would be a lovely constraint.
It's one of the constraints that we find a lot in bootloading on, say, ARM platforms, is we just don't bring up the DDR subsystem.
Yeah. I haven't yet thought at that level, at a low levelness. It would definitely be an interesting factor, but of course this is just a binary seed. You actually need much more memory to actually work. You have to compile things. Of course, you can imagine that this compiler is not optimized at all, so it will generate very long programs, and surely very inefficient. And but yeah, 6K is actually the best number that they managed to do. I mean, for me, it would be K if that was 32 bytes. The point is I'm not able to write a compiler in 32 bytes. And I did some code golf on that program, and that's the number I've reached so far. That's the reason for the number currently.
Looking at your constraints for G, it starts to feel like you are reinventing Forth.
Somehow there are if you go on the pages about if you go in the communities about bootstrapping, bootstrappability, there are many calls for what should be the ideal language for doing this kind of thing, and definitely G is probably quite similar to Forth. I didn't know Forth when I started working on G, and actually one of the reasons I wanted to work on this thing was actually to learn something. So it was the occasion also to try myself to see what's the requirements I want and how to reach them. I've looked at Forth. I don't think it would really equivalent. I mean, I don't think it's as good as G for doing this kind of things, but I haven't given this really a lot of thought. By the way, I also have a simple example of what is a G program. And you see side by side a G program, and on the right it's equivalent C program. And you can see they're pretty similar one to the other. I mean, you can map quite obviously one to the other. And that's, for me, it's an important thing when writing in G, because I think in C, and then my finger convert them quite nearly automatically in G. I'm not sure that Forth would be as really like that, but maybe I do not know Forth enough.
Not. Probably not. I'm just saying that because there are Forth compilers available written in assembly for i386 or whatever, and there are lots of Forth libraries, of course.
Yeah, but the point is that I've also, that 6K numbers, there are also the fact that I really tailored the compiler over what I wanted. And for example, the compiler does not have an intermediate format, does not have does not relocate. I mean, it loads the program already relocated in the place of the memory where it's going to be executed. It's really tailored for this problem, because my main criterion is the number 6K should be as little as possible. So I don't think that anything other than a custom solution here is going to really well optimize in that sense. Please.
Just a quick question. The stage 1 works looks amazing. This is incredibly interesting. But would you extend the project or the idea to within Debian to do what Gentoo did with, like, you know, compiler optimizations and C-flag changes? Is that a direction that, you know, you would go with saying I'm bootstrapping from compiler all the way out to infinity with rebuilds, or?
You mean I'm not sure I've understood the question. Is it ISMC related or for the other steps?
For the other steps, so
Okay.
like similar to like what Gentoo does, they have a stage 1 that's similar to this except much larger, but then they use that stage to build everything else.
Yeah, that's basically my idea for the later stages. So which is basically actually maybe more clear to where NBS is doing right now, which is, as I said, start with a TCC and Musla environment that is as little as possible. And then you try to begin compiling other programs. Of course, you are in a very restricted space. And, well, I'm not yet to the point where I have more than one stage because I'm still working on the first stage. But ideally, that's what should happen. I mean, I begin compiling Dash, Make, M4 from FreeBSD, then there is Flex and Bison. And at some point, okay, I have this collection of half crippled programs because I have to do hoops to be able to compile them. I'll do another stage where I try to compile them properly, and if needed, other stage even more, depending on what's required.
It's impressive work. Thank you.
Thank you.
And do you know which would be the size of the binary if you try to make a really, really simple C compiler? And that would kind of works in the same way that your G compiler did, but for C, which would be the size difference?
I haven't tried, so I don't know for sure. There are other people that have tried to implement a C compiler in assembly. At least for the projects I know, they're not directly comparable with my project because, for example, they assume a kernel. So it's different from many point of view and target ELF, not directly a loaded program in memory. And I think, and also, of course, when you go to C, they are not strictly conforming C compiler. So it depends a lot on where you cut in C in how much do you conform with the C standard. But they claim to be around. If I'm not wrong, like tenths of kilobytes. I'm just off my mind, but we can work it out after we finish. But that's more or less the idea.
Okay, thank you.
Thank you. And yeah, if there are, of course, I mean that's. I think that all of this is very interesting, and I think that the target is very hard, but it would be very nice to have. So I mean, if you feel you like this challenge, there are a lot of projects as I shown you. And so feel free to enter. Definitely, everybody of us is always look for patches and helpers and whatever. So well, feel free to come. That would be absolutely awesome. And let me just finish, since I think I have no more than a couple minutes left. I would like to show, maybe just to brag a little bit, if what ASMC actually does. When I ran it into the pipeline, the CI. So very quickly, what happens is that well, apart from some setting up, yeah, I believe that it's not that legible, but GitLab won't let me doing much, but. So there is some some boot up. This is just loading, and here the ASMC payload is actually booted, and it basically starts compiling G programs. And you can somehow understand what they are about. But basically, there is memory allocator, a vector implementation, some red-black trees, and some drivers. And at some point, there is an assembly compiler and a C compiler written in G, which is a terrible C compiler, by the way. But it's just barely enough to compile TinyCC compiler, which is a better, definitely. So here is the preprocessing, here the compilation. Once we have TCC, ideally what I would like to have is to compile Linux. I'm not there yet. I'm learning how Linux compilation and Linux loading works. For the moment, the only thing that happens is that I'm able to compile a patched version of iPXE, and that's enough to have some network drivers, which, I mean, are not really fundamental, but it's already something, and that's what currently ASMC does. Thank you very much for coming. I think we're over, and see you around.